This video shows how to create a column-column flanged splice joint in the structure that we saw in video 10, which discussed importing a FEM model into CSE and searching for JNodes. We will work with the JNode AK, which is hierarchic and does not contain attachments. Let's look at the renode associated with JNode AK, which is the only one currently selected. The JNode occurs several times in the structure, but we only need to build and check one of its associated renodes. Initially, only the members are present, which here are in contact, because no rigid offsets have been defined in the FEM model. First of all, we shorten the slave member to create the space to insert the plate. We insert the first plate. We select the point of insertion and click on the point to which it must correspond in the scene. We obtain the second plate by copying the first one. Now we apply the world layouts. We apply 10 mm thick welds to the various edges of the member's terminal section. We adjust the thickness of the welds on the web. And then insert the layout. We apply another weld layout to the other member. Finally, we add a bolt layout to join the two plates. When the face on which the screws are to lie is selected, CSE automatically recognizes the objects to be drilled according to their position. We choose the bolt diameter and class. We define the arrangement. We want the bolts to work on a shear and tension basis. We also want to evaluate the compression on one of the two plates, so we use a bearing surface polygon. We define the constitutive law for the support material. From the four nonlinear no-tension laws, we will use the unlimitedly elastic law, specifying a homogenization factor for the bolt's modulus and a suitable maximum sigma value in the current unit. The maximum sigma value was obtained by considering the pressure that would cause the yield stress to be reached in certain critical parts of the plate, as shown in the pop-up. We select the bearing surface. To keep things simple, we allow compression to occur all over the plate's surface. As seen in the previous video, CSE enables bearing surfaces to be defined more accurately in accordance with the standard. We also define the objects whose bearing surface will be checked. We apply the layout. We check the connection for consistency and for overlaps. The objects do not overlap. All the components are connected correctly, so the only chain present in this case is shown. This is the only possible path between one member and the other. We modify the lower plate and tell the software to automatically create the FEM model. We keep the default parameters for the mesh properties. We set up the checks without going into the details. This dialog box is used to choose, among the other options, the reference standard, the safety factors, the methods of computing the internal forces, the checks to run, and the check of the component shifts. We select Eurocode. And we set the checking combinations as those from the imported FEM model. There are 48 combinations for each of the 16 instances of this node, so, in order to expedite the computation, we ask the system to pre-select the combinations that maximize the internal forces. Forces acting at the same time in the set of all combinations will also be considered to do so in this pre-selected subset of the combinations. We want the FEM model of the plate to be created and analyzed automatically. Let's check the connection. The FEM model of the plate is created automatically as requested. Now the static analysis of on the model is automatically performed. The checks have been completed. The results listing, if requested, is shown automatically, and now all the post-processing commands are available to analyze the results. The bolts and welds, in particular, have been checked in the various combinations and instances. One thing we can do is compare the plate checked using the FEM model and the one that underwent the bearing surface check. The maximum utilization given by the bearing surface check is comparable to that from the analysis of a sophisticated FEM model that includes the state of stress in the plate, based on the forces transmitted by the bolts, the welds, and the bearing surface. Let's look at the current results. We can go to combination 2, for example. If we inspect the utilizations, we see that the values for the two plates are very similar, even though they come from different checks. Moving to another combination, number 7 for instance, we can inspect the utilizations again. Let's now look at the FEM model created automatically for Sargon by CSE, which we access directly using the command provided. Since we asked the program to automatically analyze the model, the post-processing commands are now available. We can look at the foam meso stresses in combination 7. The ratio between the maximum von Mises stress and the yield stress is equal to the utilization value that we saw earlier in CSE.